All right, let us know when you want to kick off.
Make sure that you change the title, Daniel.
We'll be starting the presentation at 11:35. Just to get everyone in here.
Yep, sounds good. How many students do we expect?
Daniel.
Oh, it's usually for the other ones, it's around 10 at most.
Okay.
But since this is mechanical, I would expect more.
Okay.
There we go. Hi, Madison. Aaron says, "Good morning, everyone." Good morning, Mr. Heyman. All right, it's 11:45. Or no, it's 11:35. Gosh, I can't read. But let's go ahead and get started.
All right, sounds good. Let me share my screen here. Let's see. Yeah. There's your screen. Screens. All right, how's it coming through?
Really good.
Okay, we'll go ahead and kick her off. So, my name's Paul Elkovich. I've been a mentor with the RoboHawks from 2004 to 2018, so about 15 years. So, just a little bit of experience there. Chuck's the only guy that's will be following up after me that's was a longer mentor than I was. So you're going to get a dose of some level of experience today. Okay, so we're going to talk today about general design concepts. I'm not going to go into detail. We're not going to discuss how to select gearboxes or details of a chassis design or even specifics around game piece handlers. We're going to leave some of that to some future sessions, and also Chuck will be getting into some of those details today. What I want to talk about is how you get from game strategy to some design concepts, making decisions about the robot, and priorities for what type of features that you want to build into your robot, and ultimately coming up with a set of specifications for that robot. So essentially moving from a strategy to making decisions to a set of specifications that allows you to then take those specifications and move forward with a detailed design for the robot. So if there's nothing else to take away from today, this is it. The robot design doesn't really start until after your team determines a game strategy, because everything within the design should be moving you closer to that game strategy. So just a kind of a quick, I don't know whether you've covered game strategy or not as one of your sessions, but how do you determine a game strategy? You really start with the game facts. In other words, on kickoff, when it's revealed, all of the game rules and scoring and penalties and all of that, that's really kind of the key cornerstone that you need to start building a game strategy. Typically, what we've done over the years is we've done a simulation. In other words, how is the game typically going to be played? And then from that simulation, we've compared it to other games. And why do you do that? It's always easier to look at something, maybe similar designs, similar games, similar strategies for those games, and use those as a basis to help you develop your game strategy for the current game. And then team experience has a lot to do with it. So some of the mentors, some of the senior students that have been through the process before know what's worked and hasn't worked for your team is also important input into that game strategy. So really the best FRC teams use an organized process to really determine their game strategy. And you want to keep that strategy realistic. You don't want to make it a pie in the sky type of thing. And you want the game facts really to determine the play. And you want to analyze and develop your game simulation, and then use that really to determine your game strategy. So really, you want to take your game strategy and you want to get to the point where you're going to build a robot. So what are the steps in between to allow you to get there? Okay. You have to make some decisions, and that's primary area we're going to focus today on. What are some of those decisions? And those decisions have advantages and disadvantages to each robot. So you kind of have to weigh those consequences and determine which of those decisions are most important to lead you to be able to execute your game strategy. Prototyping. If there is one key characteristic of your robot that you're banking on in order to be able to execute your game strategy, you're going to want to prototype that. You're going to want to prove that concept. You're going to want to ensure that that's going to allow you to execute your game strategy. And then also, before you get into actually designing your robot, you're going to want to come up with a set of specifications. And we'll show you what that looks like and the important features of it. Because before you can go through and do calculations on robot speed, things that are key to you executing your game strategy, you need to know what those specifications are. And then you can go into the detailed design process that allows you to then begin robot construction or build. So again, we're going to talk today more about what those decisions are that are important, and not only decisions, but priorities on robot characteristics, because you may not be able to get everything you'd like to have in that robot. So what are the most important ones that allow you to execute your game strategy versus ones that are like nice to haves, but not necessarily key to executing your strategy. But all of the team decisions need to support the game strategy and build on it. Okay, so let's jump right into it. So what kind of decisions are we talking about? We're talking about really decisions that are physical characteristics and operational characteristics for your robot. Operational characteristics, things like robot speed, things like if your task and your game pieces are, say, balls that you're putting into a goal, how many of those do you want to be able to put in the goal per second or per minute, or some sort of operational characteristics that you want to design into that robot. And many of those decisions have both positive and negative consequences. And that's what we're going to go through, some of the pros and cons of those decision points today, so that you have a feel for how those can have those types of negative or positive consequences. And in many cases, you need to weigh the positive versus negative impact. And where you have a negative impact, but it's a very important feature that you may want in your robot, then you have to develop mitigation for that negative effect. And we'll show you some examples of that as we move through this presentation. So what are some examples of some of these design decisions that you may need to make? One of them is maximum robot speed. How fast the robot, when the throttle's wide open, do you want it to be able to achieve? Wheel size and type. Wheel size doesn't sound like it's an important aspect of the robot, but it certainly is, and we'll show you why and how different types of wheels are used in certain circumstances. Robot wheelbase, and we'll show you what that is and why that's important. The shape of the frame could be important depending on the task at hand. Robot height is important. Game piece storage. again, that's going to go back to the game. It may or may not be allowed. Sometimes you have a limited storage. You can only be allowed to store, 3 pieces, 5 pieces. Some of them it's unlimited, so you can, store up to 50, 75, 100 game pieces or game elements on your robot. Game piece delivery, speed, range that you want to be able to deliver them from, and level of difficulty. In many cases, the game pieces can be delivered into different goals, some of them more difficult than others to deliver them. And part of your strategy that you develop will tell you what level of difficulty. And usually there's trade-offs. The more difficult goals have a higher point range, but they also may take more time, and you may opt to forget about the most difficult and concentrate on the lesser difficult ones, because from a speed perspective, if you get 2 scores in a high goal or 3 scores in a medium difficulty goal, it may be more advantageous to go for the intermediate difficulty rather than scoring in the most difficult goal. Okay, let's talk about robot speed. So a fast robot, and I would say even very fast robot, travels in the range of 15 to 20 feet a second. In our years, we have designed some to be in the 20 to 20 plus range. That's a very quick robot. If you think about it, in literally 4 to 5 seconds, you can accelerate and be from one end of the field to the other, which can be good. It also has its negatives. So the positive side of a fast robot is it is able to move quickly around the playing field. When would you want to do that? If you have to go to one end of the playing field to pick up your game piece elements and traverse across the field to be able to score those into your goal, moving quickly around the playing field is advantageous that you have a fast robot. It's also good for a blocking type defense. If you can beat your opponent to a specific spot, and maybe that's a constrained portion of the field, and set yourself in a position where it's difficult for them to get around you, that could be advantageous from a defense perspective. And advantages of a fast robot is if you have a very quick-paced game, you have an advantage. So what about a negative impact relative to a fast robot? If you have to make precise maneuvers, it's very difficult with a fast robot because your joystick control has to be very, very fine to be able to do that. Now, again, there are ways that you can, within your programming, change those characteristics that allows you to be more precise, or you can do things like a 2-speed transmission as well. Will allow you to have a high speed setting and a lower speed setting. But again, does that make sense? 2-speed transmissions typically add weight. Do you have the ability to, take that additional weight with a 2-speed transmission? Negative impact, stability. If you have a tall robot and a very fast moving around the playing field, you could have issues with the stability and the potential that robot tips over. You don't want that to happen because if you tip over, the game over from your perspective. So stability is one of the most important things that you want to have in a robot. You don't want to be on your back watching the rest of the game take place around you and not be able to participate in it. Also, a robot that has very quick speed has a lack of pushing power. So again, a 2-speed transmission would be advantageous because you could go into low gear and still have that pushing power. But in general, fast robots are lacking the ability to push another robot around. Also, moving around the field very quickly, you're prone to collisions because you just can't react fast enough to potentially avoid those collisions. So again, it could, it's going to happen if you have a fast robot. So you need to then also build a very robust robot so that it's able to withstand those collisions. Okay, if anybody has any questions, please feel free to chime in or use the chat box, and we'll try to answer them as we go through. Okay, robot wheelbase, what is that? So here, a very simple schematic of a robot. Wheelbase is the distance between the furthest forward and furthest backward wheels. In this case, it's kind of showing a 4-wheel robot. You also will have a 6-wheel robot. Your middle wheel would not come into the play on your wheelbase. Your wheelbase is determined by your furthest forward and your furthest backward wheels. So we're going to start with a long wheelbase. What are the positive impacts of it? It helps with robot stability. So again, if you have a tall robot where your center of gravity is not very low within the robot, it helps with stability. Also, if you have ramps or uneven field to go over, a long wheelbase helps you go over those in a stable fashion. And if your robot has to extend, say it has to extend out to be able to pick up a game element, it's important that you have a wider wheelbase. And we'll show you some examples of that or some schematics and on how that looks and how that works. So what's the negative impact of a long wheelbase? Predominantly, it reduces your maneuverability. It's more difficult to maneuver in tight spaces with a long wheelbase. But again, there are also some mitigating factors like a 6-wheel drive that lets you spin in place and don't have to, it doesn't impede your maneuverability as much. To maximize your wheelbase, you really need smaller diameter wheels, and I'll show you that here in a minute. But those small diameter wheels can be negative depending on the field obstructions that you have to navigate in the specific game. So here you can see how a smaller wheel expands your wheelbase. So this is kind of an 8-inch wheel versus here a 4-inch wheel. You gain 13% in wheelbase just by using a smaller wheel. But again, is a smaller wheel, does that give you the sufficient capability to go over the field obstructions that you may have in your game? So here we're going to look at the impact of wheelbase if you have to extend out. So this is just showing an example. You got a game piece that maybe weighs up to 10 pounds. You're reaching out. You have a robot that has a certain wheelbase with a certain center of gravity. And then you've got, because you're reaching out so far, you've got a specific moment arm. And in this case, your front wheel becomes the fulcrum point where you're pivoting about. So the weight of the robot in its center of gravity is offsetting that moment arm and the overhang that you have related to the game piece and its reach. So now if we again go to a smaller wheel, increase our wheelbase, you can see how that reduces the moment arm. Everything else on this, in this sketch, is the same. The same distance out from the robot, but you can see it significantly reduces the moment arm or the weight that's trying to tip that robot over with that center of gravity. Another item is ramps. And here, this is just kind of showing a tall robot, and assuming that the center of the gravity was equally distributed within this robot, this would be a problem. Now here you're pivoting about the back wheel on your going up the ramp. Your back wheel is your point of your fulcrum, or your point of rotation. And if you had, in this case, a very uniform center of gravity, you'd be in trouble. You'd be tipping over, because you can see the red. There's more red on the negative, on the downhill side of that pivot point than there is and the white on the positive side. So does anybody have an idea how else besides wheelbase you can influence the stability of the robot? Anybody keep an eye on the chat box, see if somebody's got an idea. Anybody awake?
Yeah, we're just, there's a little bit of a delay, so we're just waiting to see if
Okay, no problem.
put anything in yet. Somebody
Okay.
said counterweights.
Counterweight, yeah. So what's that counterweight really doing? It's changing the center of gravity. Okay, you see that middle robot. It's pushing the center of gravity of that robot further back in this case. And by moving the center of gravity of the robot, a counterweight is a way of doing that. It definitely can help the stability of that robot. So good answer. Good answer. Okay. Okay, so another decision that has to be made on a robot is what type and size of wheel are we going to use? Okay, we already said that in the case of smaller diameter wheels, it helps your wheelbase, because usually you have a limit on the size of your robot. And in recent years, they've done it with a robot perimeter. In past years, they would give you a hard length and width that you couldn't exceed on a robot. So wheel size definitely has an impact on that. Okay, so let's start with large wheels and talk about the advantages of large wheels. So it maneuvers obstacles easier. In other words, a small diameter wheel, if you have to go over a large obstacle, can actually, in some cases, stop you from being able to maneuver over that obstacle. It also increases your ground clearance. So you can see the robot on the left at the bottom versus the robot on the right, how that ground clearance changes. And ground clearance is important for ramps, because if you have a ramp where the top edge of that ramp comes into play, you may need more ground clearance. In some events that we've seen over the years, there may be pipes across the bottom of the field. There may be tracks that they have where there's electrical power getting to certain field elements that you have to navigate, and you may need a certain amount of ground clearance to be able to maneuver those. The other advantage of large wheels is it helps you if you don't have a robot with any extension. So if you don't have to extend out, you don't really have to worry too much about the use of large wheels. But if you do have to, it becomes a disadvantage for you. So negative impact, as we already said, large wheels will shorten your wheelbase. It also raises your center of gravity. So here was our robot in 2016. It was a game called Stronghold. And the robot is actually going over a 6-inch square steel field obstruction. And you might look at that and say, wow, how are they doing that? Those are 4-inch wheels that they're using, but they're going over a 6-inch pipe. Anybody have an idea how we were able to do that with this robot? Maybe some of you, Chuck, I know knows, but some of you that may have been or not involved in that years, any thoughts on how we were able to traverse that?
I would think by using some sort of a counterweight measure to kind of swing yourself over it.
Any responses? Otherwise,
There's no responses right now.
Not that I see.
Okay. Oops, I went the wrong way. Here we go.
Wait. So, someone says, were you able to extend/retract the wheels?
Yeah, no, we weren't. But here's the way we did it. We actually embedded above the wheels, we had a product called a Rhino tread, basically like a Caterpillar track that actually was sitting above the wheels. So when we were on flat playing field, we were driving on our 6-wheel drive. But when we had obstacles like that 6-inch square pipe or tube that we were going over, the Rhino tread allowed us to lift and go over obstacles such as that. So this is a way that we were able to have the stability, the small wheel size that gave us all the advantages of it, but we were able to integrate another way to mitigate the effects of that and be able to get over some of these different obstacles that this particular game had, and it had plenty of them. This just happens to be one of the most severe ones that we had. Was this 6-inch steel tube, but there were other obstacles similar to it, and that track allowed us to do that. Okay, so robot wheel size and type. We're going to get into a little bit more details on that. So here's many different types of wheels that are available from robotic suppliers to be able to use. What is the primary difference in these wheels that you might say are characteristics? And these all happen to be about the same size. They all look like about 6-inch wheels. But there are other things that are differences. And can you give me some ideas on what some of those differences might be? differences other than color.
There's the internal structure of it, as well as somebody in the chat said the grips on them.
Yeah, yeah, and that is key. So grip we typically would call traction, right? That's the term that you would use in your car, the amount of traction that you have. And the main difference why the two wheel types on the right are used are for maneuverability, okay? They allow you to do things that the wheels on the left don't allow you to do. And that traction is, and we'll get into the details of it, is a function of the coefficient of friction between the wheel and the surface that it's on. And you can see here that the first wheel has a coefficient of friction of about 1.0, and the wheel in the middle has a coefficient of friction of 1.3. So it's a pretty significant increase in its tractive ability, which is important for many different reasons. But if you're playing defense, you're pushing power, or if you actually have game elements that you have to push around the field or move, you want to have more traction capability. Acceleration, rather than the wheels slipping, you have more tractive effort. And you can see in the two wheels on the right, they have a different coefficient in the different directions. So in other words, the one, the fourth wheel there, that has a coefficient of friction of somewhere between 0.8 and 1.0 in the forward direction, but sideways it's 0.2 or less. So that allows a robot, if you use those on, say, a six-wheel robot, six-wheel drive, on your front and rear wheels, it allows that robot to turn very freely. You don't have to drag those wheels. It can spin very easily around the two center wheels. The wheels far on the far right are what's called mecanum wheels. And those give you very high degree of maneuverability. And depending on how you spin those wheels in conjunction with each other, that robot can physically go sideways, forwards, backwards, and sideways. And so if you have a game where you have to maneuver very finely in position, that may be a big advantage to you. It allows you to go up to that goal or field element and move left or right without having to move forward, turn back. You know, it allows you to not only go forward and backwards, but sideways. So what's the advantage of traction? Again, it's pushing, it's climbing, it's acceleration. There are two components to traction. One of those is the coefficient of friction. Does anybody know what the other one is?
Somebody in the chat said the normal force.
Yep, normal force. So on a flat surface, that's the robot weight. Okay. So a heavier robot with a high traction, high coefficient of friction wheel will have better, more pushing power capability than a lighter robot. So depending on what your game strategy is, you may want to have a heavy robot with good traction, but a heavy robot is harder to accelerate. And a lighter robot accelerates faster. So you can see some of the trade-offs in the decisions that you have to make relative to types of wheels, size of wheels, weight of the robot, how all those things can change the characteristics of your robot. So the simple formula, again, your tractive effort or your tractive force that propels your robot is equal to the coefficient of friction times that normal force. And on a flat ground, that normal force is the same as your robot weight. And that tractive force is what allows your robot to propel itself. So why is coefficient of friction important on inclines? Anybody know?
So that you can climb up the incline and not fall back down.
Yeah. So if we look at it, here your force of gravity is always straight down, right? Your normal force in this case is only 0.87 times your force, but the force trying to pull you back down because of being on an incline is actually half of your weight. So if you kind of solve that, if you don't have a coefficient of friction of at least 0.57 on a 30-degree ramp, you're never going to be able to navigate it because your wheels will just slip. Your force pulling you back down will be greater than your tractive effort. And that's why on ramps, coefficient of friction is so important. Now, the other thing that I guess would be probably the next step that we need to talk about is what is friction coefficient or coefficient of friction? Anybody know what that is? I think I'll just move on because we got a lot of material to cover. But friction coefficient is the gripping interaction between two surfaces. So the coefficients that you saw in the earlier slide, those were the coefficient of friction on carpet, which is the primary surface of the field on the FRC playing fields. However, that's not the only surface. Typically, they have ramps or other surfaces that are hard plastic, even hard slippery plastic, and your coefficient of friction on those surfaces is different because you've changed one of those surfaces. So ultimately, if your playing field surface changes, so does your friction coefficient. And you may need to actually test different wheels, different tread surfaces on a hard slippery surface to ensure you have enough traction. And you may need to compromise. We've built robots where we have some wheels of one tread material and other wheels with a different tread material in order to have sufficient coefficient to allow us to navigate the game fully. So you can't just say, hey, these wheels have the best coefficient, because they may on carpet, but they may not on some of your field elements that you might have to navigate. So you kind of always have to look at that. and use that as part of your determination as you're getting into the specifications on your robot. All right, let's talk just a little bit about game piece handlers. Game piece handlers are related to your game pieces, and sometimes they're balls, sometimes we've had them be cubes, we've had them be many different shapes and elements of it. But I like to group them into two different categories of game piece handlers, and then you want to have different characteristics depending on the volume of those game pieces that you have to handle. Okay, so low volume I call less than 10 pieces. So if you're going to only touch 10 game pieces in a match, you want to have a highly effective way to bring those game pieces into your robot. You want to protect them when you carry them, because you don't want to have somebody bump into you and you lose it. Now you got to go back and pick up another one. You want to have a very high scoring hit rate, and you want to build a robot that's pretty darn accurate and efficient. If you have high volume, I mean, we've had games where literally we would bring into our robot and exhaust well over 100, maybe 150, 200 game piece elements. There, it's all about speed. If you lose a few, your accuracy is 80% versus 100%, but you can put them up there so fast, you don't have to worry about being quite so efficient. If you get bumped into and a few of the game pieces spill out over the side of your robot, okay, no big deal, because you're dealing with literally tens or hundreds of these game pieces during the match. So again, if you have a very low volume, you got to make sure that each game piece, and in some cases, you're only allowed to carry one at a time. So you want to make sure it's well protected, because you don't want to lose that game piece, and you want to be as close as you can to scoring each and every one of those game pieces. So the game rules will determine your play, and then you have to analyze and develop a simulation to allow you to get the right game strategy. Okay, so here was our 2018 robot. This was a game called Power Up. So the 346 robot is on the left. There's another robot, 4541, on the right. And you can see there's a pretty different, even though there might be a pyramidal shape between the two robots, the way that we approached the game was pretty significantly different. So what we did was we actually shot the cubes. So we sucked them into our robot, and we shot the cubes up onto this large teeter-totter scale type of a mechanism in the middle, and that was how you scored points. You didn't score points by putting them up there, but what you wanted to do was keep the teeter-totter tipped your direction. So you wanted to have more cubes on your side of the scale so that it tipped your direction, and for every second that you had it tipped in your direction, you gain points. And you can see what our approach was there, shooting those cubes up there. So our strategy was to be very quick, get around, get these things, shoot them up there, and gain advantage very early on in the match. Even our autonomous, we were able to get on a consistent basis 2 cubes up there during autonomous, and on rare occasions 3 cubes up there, depending on your starting position and how well the robot executed. End game was a hanging from a crossbar. Here you can see the end game. where we were. So if you were to compare the 4541 robot against the 346 robot, what are some advantages that you think we had in our design versus the 4541 robot?
Somebody had said speed.
Speed, yeah, we had a pretty quick robot. We didn't have to take a lot of time to extend, like the robot on the right, the 4541 robot, to be able to deploy the cubes. They probably had an advantage for being able to more precisely place them than we had. But what our strategy was is to get as many cubes up there as fast as we could. And filling that first layer was pretty simple because there's a backstop on that platform. So we could throw several up there very quickly and get the advantage and tip it our way. Later on, they may have had the advantage because they were able to place them on the, say, like the second layer better than us. But by the time they got to that stage, we already had a big point advantage. So another advantage that we had, picture 4541 where they're picking up cubes off the field. So they would lower that mechanism that you see at the top there down. And the way that they carried the game piece was outside of their robot in front. So if you were playing defense on them, you could bump into them and likely discharge that robot or discharge that game piece from their robot. In the case of ours, the game piece was fully within our robot. Nobody could discharge ever a game piece from our robot. So a defensive strategy against us was not very effective because of the way we were able to keep the game pieces in our robot, and also our ability to move quickly and be able to get around the field. Okay, so we're getting near the end here. So here again are some of the design specifications that you're going to need to think about. Okay, we talked about robot speed. You know, do you want somewhere around a normal speed, or do you want a very fast speed? And again, there's disadvantages of it if you have to do fine maneuvers with the robot. But again, there's also mitigating ways to do it as well. So you got to think about that. The aspect ratio of your robot. Do you want a wide robot because you want to have a wide harvester to pull in a lot of game pieces as you drive through them? Or do you want to have a narrow chassis? Wide robots, not very maneuverable. You got to think about your wheel composition. Do you want traction or do you want maneuverability? Game pieces, the storage. I mean, the game may define it. They may tell you can only have one game piece at a time. Then that becomes clear. Your target. Do you want to go after the most difficult goal, or do you want to go after an easy goal, or maybe an in-between goal? A few years ago, we took kind of the middle of the road. We said we could shoot the easy and the middle, but we weren't going to take the time to shoot at the top goal, which was the most difficult. And that turned out to be a very successful strategy because speed was in our advantage. And you also have partners, so you don't have to do everything. So you picked a partner potentially that was able to get the upper goal. You concentrated on the lower two and were very successful because of that. Game piece delivery speed. You know, when you have maybe 100 or 200 game pieces that you're going to touch, you got to be able to deliver those very, very quickly. So in the case of one of our matches, we were shooting for 5 balls per second is what we wanted to be able to put out. And we ended up having to use 2 shooters to be able to do that because we couldn't get 5 per second through one shooter. So we actually had 2 of them shooting balls in order to be able to achieve what our target was for delivery of game pieces. You got to think about the delivery of those. If you're shooting balls, how far away am I going to shoot from, and what is my delivery accuracy? The further you are, the better aiming you got to have. You also have to think about those balls are not always perfect. They get run over, smashed, cut, and then that has a direct impact on how accurately you can shoot them. Autonomous function, end game functionality, all of those are important and part of your specification that you want to design into your robot. Just a few design principles. Obviously game strategy is the most important thing that you have to understand and know what your game strategy is before you begin designing mechanical concepts. Your strategy should focus on efficient gameplay, targeted tasks that control the game, the tempo, the flow of the game. When at all possible, you want to rely on proven designs. That's why we would always, during the weekend of kickoff, we would have students go out and look at past games and look at designs they use to do similar functions that you want to have in your game strategy. If there's a key function that you need for your game strategy, you're going to want to prototype it. Make sure that it's feasible to do what you want to do. And again, those game elements change and wear, so those are going to potentially affect the range and accuracy that you want to be able to deliver those game pieces from. You want to really strive to overperform, not struggle to achieve. Human players are extremely important. They must practice, they must get it right. We've seen so many matches where maybe they're putting game pieces onto the field, and if they don't practice, they don't go onto the field right, and they become negative for a team because now the robot can't pick them up because they didn't fall in the right way that the robot was designed to be able to pick them up. We've seen a lot of errors, so the human element is extremely important. When you get into mechanical design, you have to do that with mind that there are electrical and pneumatics potentially, and you have to leave accessible space for them. And it's always an advantage if you just keep the weight down low on a robot and keep your center of gravity low. So if there's nothing else, again, to take away from today is your robot design starts after your team determines the game strategy. Okay, that's all I've got. Chuck, I think you're next.
Yes, we will move on to Mr. Chuck's presentation, and then we will have just an overview and if anybody has any questions afterwards.
Yep.
All right, you ready for me to bring mine up?
Yes, sir.
Yes, sir.
Okay.
So if there's any questions while Chuck's bringing his up, they can go ahead and pop them out there.
All right, mine's going to be about tips and information on motors and gearboxes. I'm Chuck Gruniger. I was a mentor for First Team 346 for 20 years, from 1999 until 2019. I was also a robot inspector at competitions for 10 plus years. My objective here is to present a typical motor gearbox combination and to discuss key information for building versaplanetary gearboxes. I will introduce some software tools for calculating motor and gear ratios for a given outcome. This is a general family tree of all the different motors and transmissions that are available through Vex Robotics that we normally use for our robot. We have the Falcon 500 at the top that can be used to directly run most of our drive transmissions. We have 3 types of 2-speed transmissions, and then we have single speed transmissions. They can use between 1 to 3 motors each. Our next is our Sim and the Neo motors that can also be used to run all of those types of transmissions. The Falcon can also be used with a short shaft through a Sim adapter to run your versaplanetary to give you your different drive outputs. Your Sims can also be run through a Sim adapter through the versaplanetaries. You have your group of smaller motors like the 555 and the 775 Pros. They can be run directly into the versaplanetaries. They can also be run through a dual motor adapter into a versaplanetary. You have 2 different inputs into the versaplanetaries. You have a 90-degree drive and you have a 180-degree drive. The 180-degree drive must be the first stage after your motor, and it is designed to handle the stall current of the motors listed in this document. The ratchet slice, used for maintaining a position like in a winch or whatever so it doesn't back off, but it should be the closest set to the motor. At that point, it's less force that must be held in order to lock the rotation. The dual motor, since 2 motors are used, you have to account for it's twice the torque going in. But there's also different gearing options in that double motor unit that further increases the torque going in. That is important for when you're doing your load ratings of the versaplanetary. To use the tables, it has 2 types of calculations: a simple load rating and a combined load rating. It's recommended to mount the versaplanetary gearbox that the simple load ratings may be used. A lot easier to calculate. The simple load rating assumes the output of the shaft has a minimal overhang, as in the socket close to the transmission or the end of the shaft is supported. So therefore, these 2 are recommended with the green checks. The unsupported shaft is not recommended because of the complications in calculating the load ratings. Also, since the 7-to-1, 9-to-1, and 10-to-1 gear sets have a lower torque capacity than the 3-to-1, 4-to-1, and 5-to-1 gear sets, it is highly recommended to put your larger ratios first and your smaller ratios last. As in this combination here, the second one is recommended because it has a higher torque capacity. With the 5-to-1 first and the 10-to-1 second, it only handles about 10 Newton meters, where the 10-to-1 first and the 5-to-1, it'll handle up to 154 Newton meters. Now, to understand the load ratings, in the tables, they use a red-green rating system. If the combination is highlighted in green, then it's within the gear ratio recommendations. If it's red, it will have a failure later on. In a simple two-stage, you can see that it's fairly, the green ones here, this is based on the mini sim. 10 to 3 gives you a 30 to 1 ratio. A 10 to 10 would give you a 100 ratio, 100 to 1 ratio, but it's in the red and not recommended. You can go to a 3-stage. The first column, stages 1 and 2, you can get from your 2-stage. And you will notice in the 3rd stage that between the 5 to 1 and the 7 to 1, there is a drastic difference when you change the order of the gears. This is where it really comes important to have your larger ratios first. Software tools. I have found it's a spreadsheet calculation. The JVN Design Calc, he was a mentor for the 148 Robo Wranglers. He stopped revising it in 2017, but a mentor for the 2412 Robototes took his design and added in the new motors and all and call it the 77 Design Calc. It is available on Chief Delphi at this web address. All this information that I've used in this presentation came from Vex Robotics /download dash search. The motor curves, all that. Additional information for the build guides are found at in the product pages on Vex Robotics. The motor curve data sheets give you the information on how much torque the motor gives at a certain speed or certain current load. All of those calculations can be found in those data sheets. That's my presentation.
All right. Does anybody have any questions for Mr. Chuck in the chat?
Whoa. Oh, did I? There we go.
All right. We don't have any questions quite yet, so we're going to move on to the next presentation.
I hope that made sense.
It did. All right. So this one is from people who are current members of the mechanical team. All right. So this one is from Madison and I, as well as Carter, who was the previous chief technical officer. I am the current chief technical officer, and Madison is probably the most knowledgeable person in mechanical who's still on the team. So we came up with this presentation just to give you guys a general overview of what we do from day to day and some of the machines and fasteners we'll be using. So the mechanical team, we're the ones who do all of the AutoCAD design, which is a program to do 3D renderings of it. we do the prototyping as well as the final design, like actually constructing the framework of the bot. And then electrical team and programming team will do all of their programming and electrical things. We also construct the practice field, which we use to help train the driver for the current year, as well as essentially build a outreach bot, which we will take to different events as outreach to try and recruit more members. So just some basic overviews of CAD. We use it to, like I said, do 3D renderings for things such as the drivetrain, which is that lower left picture. We use specifically Autodesk for our team, but if you join FTC, which our school also has one of an FTC team, they use Fusion 360, which is a slightly different program, but still has the general concepts. So some basic sketches are like a part for that would go on the bot. So you use different measurements and everything to just put it together, and then you'll extrude it. So this is an example of a 2D sketch right here. Some basic extrusions. So you would go to the 3D model tool after completing your 2D sketch, and you would use the extruding tool, and then you would type your extruding distance. So it would turn the two-dimensional object into a three-dimensional part. And a more complicated version of this is what you see right here, which is a fully completed assembly for a robot, including the bumpers, motors, electronics, and air tanks as well. So now we're going to move on to some commonly used machinery that we use almost every day that we are in the shop working on the robots. So the bandsaw is by far the one that we use the most. We use it for cutting aluminum, polycarbonate, which is the Lexan sheets, wood, and then tubing as well. So we have, in our shop, we have two bandsaws, a golden one and a green one. The golden one is for wood only, and then everything else, which is the aluminum and polycarbonate, gets cut on the green one. Next, we use the drill press fairly often. It's a very accurate piece of machinery to drill precise holes without having too much sway side to side, and it does it perpendicular to its base plate. The one that we have in our shop can drill through aluminum, polycarbonate, and wood. The milling machine is a piece of machinery that we have for precise drilling, essentially. It's manually driven, so you would go across the part manually. However, to use this one, you do need to have different training than just being safety trained. And the current person who does that is Mason Davis, so you would have to get with him if you're interested about learning how to use the milling machine. We also have a belt sander. This is just to get rid of any edges that could be sharp on the robot, because per the rules of FRC, we're not allowed to have any sharp edges on the robot. So we're not sanding the plastics on this. It's only wood and aluminum. Next up, when we're creating the practice field, we use the chop saw a lot to cut wood, just to get them to the lengths that we need in order to construct the practice field. This is a miter saw, and it just cuts it at a 90-degree angle. And you can get it to be exact degrees so that it's square properly. The last machine that we use fairly frequently is the CNC router. We use this for our chassis because we want the holes to be very accurate in where they're placed. And this uses the AutoCAD drawings as well as additional software and programming from the current person who uses it is Carter Walker, who's the previous mechanical director, and me. And we use this in order to just cut precise holes, as well as complex designs that would be harder to do on the milling machine. Madison will now take over the tools and fastener part. Madison is having technical difficulty, so I will be taking over the tools and fastener part. So some of the basic tools that we use are some Allen keys, hex keys, or Allen wrenches. Those are the three main ones that you will hear people talking about. And you will use them to turn mostly bolts, as well as a few of the other parts on the robot that we use. I believe Madison is back if she's ready to talk now.
You hear me?
Yes.
All right, cool. Did you already go over Allen wrenches?
Yes, would you like to go over them again?
No. Okay, so this is a pop rivet gun. Most people don't know what this is before they come into the shop. It's not a very common thing used outside. Like, you're not going to see like your dad using this in the garage, most likely. So most people don't know what this is when they come into robotics, like first time being in the shop. But we use these a lot just to like attach aluminum to aluminum most of the time, or like polycarbonate to aluminum. It's just something that's a lot easier, and then if we want to take them out, we just have to drill them out, and it does no harm to any material we are using. We use zip ties a lot. Sometimes they're called zip ties, cable ties. We shouldn't use them a lot, but we use them a lot for like electrical and like organizing the electrical systems and wires and stuff like that. But one thing most people don't know what it is this zip tie gun. It actually tightens and cuts the zip ties for us. It tightens them better than we can by hand. So that's really nice when we want something to be super tight and we don't want it to come off. And it's just a lot easier to use and faster. This is a chain breaker. It's a weird tool, and I know a lot of people don't know what it is. It's something that you see it and you wouldn't guess, oh, that's to break chain. But we use this a lot, usually like during mid-season to change out our chains or put new chains on the robot. It's if you look down on the left, see the little pieces that connect each chain together, and the tool actually pops out those pins. And that's about it for that tool. These are wire strippers. I had freshmen from last year, which are now sophomores, tell me that they didn't know what wire strippers were when they first came into the shop. So here's some certain pictures. The ones on the right are actually more fancier wire strippers, and the ones on the bottom left are just basic wire strippers. C-clamps and vice grips, they're basically the same thing. I would say that they're the same thing, but C-clamps are used for a lot much bigger material. We use these a lot when we're prototyping and we don't actually want to fasten something down with a bolt, like drilling a hole in something that doesn't need to be drilled into. So we use clamps a lot, and we also clamp down a lot of materials, which I believe they went over in safety training. If you use like the drill press or something, you want to clamp down the material that you're using so that it doesn't go flying when you actually drill through it.
All right. Are there any questions on anything that we've gone over for any of the three presentations? All right. If there's no questions, the last slide is just our sponsors from last year. Other than that, that concludes the mechanical team's presentations.
Well, thank you everyone for coming, and I wanted to give a quick shout out to pretty much everyone who presented today. Thank you for presenting. This pretty much wraps up all of the mechanical section of RoboU. I will now be playing the safety video from the first week. Again, thank you all for coming, and thank you all to the presenters who, presented for mechanical.
Our
I hope
pleasure.
you guys have a great day.
Thank you.
Thank you.
Thank you all for coming, and thank you all to the presenters who, presented for mechanical.
Our
I hope
pleasure.
you guys have a great day.
Thank you.
Thank you.
Uh-oh. Might be having some technical issues.
Or like general PPE guidelines and how that is going to affect us with COVID-19 going on. So it's important to note here that we don't have a full set of guidelines from the county yet. We're still working on all of that. So this is just our general setup and what we'll be doing. And you can go ahead and just put everything up on the slides then. So we have PPE that's required at all times, and this is again just for a general shop, and then we're throwing in like all the COVID-19 guidelines that we're setting up right now in there. So safety glasses at all times in the shop. Those have to be clear and see-through. You can't have any tinting in them at all. We have to be able to see your eyes. Closed-toed shoes are required at all times in case you're dropping anything. They don't have to be steel-toe. I would suggest something steel-toed just in case you roll something over your foot, you drop something on it, but closed-toed at least required at all times. Hearing protection is required on your person at all times and used when you're running loud equipment. Again, I would suggest using it when you run any type of equipment. You'll hear constantly people complain as life goes on, they lose their hearing and they'll blame it on being in the shop, being around loud machinery. So wear your hearing protection. And then obviously a mask will be required at all times in the shop. At no time will you be able to take off your mask. If you are in your car alone, that's probably the only time you can take your mask off. But if you are in the shop with other students, you have to have your mask on. When you're within 6 feet of another person, you need a face shield. So we're going to be getting close and working on the robot. We're going to be within 6 feet. So you're going to have a face mask for that. No jewelry of any kind is allowed. No rings, necklaces, earrings, any of that is allowed. Rings can get stuck in machinery and pull your fingers off. Your necklaces can get stuck in something spinning and pull off. No like lanyards around your neck or anything like that. Long hair has to be tied back, preferably in a bun, not a ponytail. A ponytail can get caught in something. Baggy clothes, you got to keep rolled up. So like your baggy sleeves, make sure you roll them up when you're using machinery because they can get caught in something.
Hey Jacob, can we pause for just a second? We're having a little bit of technical difficulty because there's music that's showing up that we're not sure about. Yeah, you can go ahead.
Can we still hear the music or no?
It's all good. Everything's good.
Awesome. Gotta love it. Okay, so yeah, hoodie drawstrings need to be tied up or tucked in because those can get caught in machinery and get yanked out too. And then that is our general PPE requirements. So next we're going to be going over how we're going to be handling injuries in the shop. So any injury to any team member must be recorded via an injury report form. These are in our binders. Your safety captain knows where that is. Mentors should know where that is too. You need to make a mentor aware of any and all injuries, no matter how minor. So even if it's a small cut can turn into something worse if it's not corrected. So all the recorded injuries will be used to improve the safety culture of the team. So we're going to use them to make changes and improve. And then our goal should be to have 0 injuries. Obviously, that's ideal, but that's what we're going to try and do. And again, before we move on, I think it's important to note, again, we don't have our full COVID-19 guidelines, but in addition to anything we show you and teach you today, there's going to be precautions made in place for that. So things are going to be kept clean. People are going to be following the social distancing guidelines. We're going to be doing whatever the county tells us to do. But today is just a general safety, what you need to know for a regular season to keep yourself safe around tools and machinery. Okay, so now we're just going to go over some general shop safety. We're not going to go into anything super, super in-depth in the general, but just some stuff to keep you safe that you need to know about. So it's important to note safety is everybody's job. So it's not just it's not just the safety captain's job. It's not just the mentor's job. Everybody has to be aware of safety. Safety isn't a priority. Priorities can change. Safety is a condition of being in the shop. It's something that goes on always. So everyone needs to consider themselves and others whenever you do anything in the shop. When you're running a piece of machinery, when someone's running on a piece of machinery, when someone's working on something, you need to be aware of what's going on and respect other people that are in your area. Make sure that everybody's following the rules. We're not asking you to be a dictator and start going around and checking everybody and making sure they're doing what's right. But if you see someone start a machine and they don't have any safety glasses on, or if you see somebody about to like lift something or move something unsafe, make sure you say something. And you can do that respectfully. You don't have to be disrespectful, but it's just important to make sure that everyone's looking out for each other and we're creating a safe environment for everybody. So just a little bit about shop equipment here. So if you haven't used a piece of equipment before, or you need a refresher, you got to be accompanied and taught by a mentor. So if you go, hey, I don't know how to use a bandsaw, I've never used a bandsaw, get a mentor and they'll teach you how to do that. So again, one thing that we plan to do, we're going over safety today, but what's super important is actually being in front of the machine and seeing it used and then using it yourself so you understand how to operate the equipment safely. And that's something once we have all the guidelines and once we figure out what's going on this season with in person, we will get that done. That's going to happen. But if you don't know, or if you say, hey, I know we've been taught on this, but I don't really feel comfortable, can I have help? 100% mentors are there for that. No one expects you to know how to use every piece of machinery. No one expects you to know how to use it for life. But if you need help with it, there's going to be someone there who can help you. So every machine has its own set of rules for safety and housekeeping. Things need to be cleaned off before and after use. Everything needs to be, done in a safe manner, and not every machine is run the same way. So you need to make sure you know what the safety guidelines are for each machine. Make sure your work area is clean before and after using the machine, or before and after working on anything. You don't want to set down a part on the top of a dirty area and start working on it. You don't want to run a machine that has a bunch of scraps in the way or anything. You want to make sure your work area is safe. When you're cutting material, like on a drill press or a bandsaw, excess waste that comes off of that is often really sharp. So metal shavings, sometimes even pieces of wood can splinter. You need to make sure that you're not grabbing that, that's not getting flung anywhere. Make sure that it's getting cleaned off with a brush. You don't ever want to use air to spray anything off. That's dangerous. It can put dust up in the air. All right, and we're moving on to hand tools. So it's important that you are using the right tool for the right job. A screwdriver is not a hammer. A wrench is not a hammer. Do not use it like a hammer. That's improper use and can cause damage to the tool and could possibly cause a tool to break and hurt somebody. You also don't want to use broken or damaged tools. So if you see a tool and you go, hey, this piece is kind of loose, this doesn't look right, the end of this is mushroomed, it's straight up broken here, do not use it. Tell a mentor when you see a tool in bad condition, or if you're unsure of its condition. If you go, hey, I don't know if should be like this. Is this right? Ask a mentor and they'll help you out. Be aware of where your hands are when you're working. I know that sounds kind of silly, but if you're holding something in one hand and using a screwdriver in the other hand to screw something into that piece, make sure that you're not applying so much pressure that you slip and stab your hand with a screwdriver, things like that. When you're drilling, make sure your hand is in the right spot. When you're putting a screw through something, make sure there's like no hand or piece of material on the other side. Make sure you put tools back where you find them. That's a big issue in the shop, is keeping things orderly. Make sure the screwdriver is going in the bin marked screwdriver. If we need a screwdriver for something, or we need a tool to pull something apart, we want to make sure we have access to it and know where it is. So, and don't leave the tools out unless you intend to use them. Obviously, if you're working on something for a period of time, you can keep the set of Allen wrenches out, next to you. But if you're done with that, try and put it back. Keeping stuff out isn't really smart. It gets in the way. We lose things. Just make sure you put things back where you find them, and treat the shop and the tools in the shop better than you would treat your own. It's important that we leave the shop better than when we found it. It's important to leave the tools in a better condition than when we found them. All right, battery safety. This is really important because obviously all of our robots are going to be using a battery. They're really more dangerous than you think, and it's important to keep them safe. When you're moving and carrying the batteries, always use two hands, never hold them with one hand. They weigh a lot, and you want to make sure you get a good grip on them. I normally put one hand on the side, one hand underneath, put both hands on both sides, whatever works best for you, but never hold them by the wires. You're just going to rip connections off, and that's a problem. Never fun for anybody. The batteries normally have a protector that goes in the in connector. It's just a plastic piece that sticks in so that nothing can get into the connector. If there is a battery that isn't connected, it needs to have one of those connectors in it. The only time that there's even a slight exception for that is a battery that's in the robot and has been disconnected for some purpose. If there are batteries on the side somewhere, if there are batteries and a charger that aren't plugged in, they need to have those connectors in there. If a battery is broken for any reason, you need to let a mentor or safety captain know. The safety captain will notify a mentor. It's not anybody's job specifically to clean up that battery spill. We want to leave that to a mentor. The safety captain will be trained on how to do that. And we have a battery spill kit located in the tool cabinet. So it's just an acid, and you want to neutralize the acid and then sweep that up. You need to use the right kind of gloves. It's something it's like putting out a fire. Not everyone is expected to use the fire extinguisher, to use the battery spill kit, but you need to know where it is, and there needs to be a person designated who's going to use it. All right, and next, moving and lifting. So this might seem kind of silly, but it's really important that when you are taking something from one side of the shop to the other, or you're moving anything around, that you're doing it in a safe manner. So you really want to plan your path from A to B. It's like, okay, we're moving these boards from, the garage doors in the shop to the area where we're working. We need to make sure that, there's not stools and stuff in our way. No one's going to trip on the way. There's not cords and like material laying on the floor that we're going to trip over. Make sure that when you are moving a large object, you are aware of where people are and where that object is, the geometry of that object. So I'm sure you've seen cartoons before where someone's holding something over their shoulder and they turn and whip around and knock somebody over the head or knock somebody over. We don't want anyone doing that. Make sure that you're aware of what you're holding, where you're moving it. When you're lifting heavy objects like the robot, you want to make sure you're lifting it with two hands and you're lifting them with your legs and not your back. I know that sounds like something you'd say to an old person, but you really want to make sure you're lifting with your legs and not your back. You can cause serious injury that way, and it's just how you should train your body to lift these things. It's the best way to do it. Okay, now we're moving on to machine safety. So this is for the specific machines in the shop. And I want to say again, this is not a substitute for actually sitting in front of the machine and running it and being taught how to run it in person. Again, we're going to try and do that as best we can with the guidelines. And if we have people working in the shop, we're going to be training them how to use the machinery safely. So just take that into consideration when you're looking at all this. These are just general safety guidelines for the machines that we use, but there is, more to using the machine. So this will teach you how to use the machine safely in a safe manner, but again, it is not in place for actually running the machine in person. So first up is the drill press. When you're running the drill press, you want to make sure that the material that you're trying to cut is clamped to the table. There's also a little vise on one of our drill presses in the shop, so whatever you need to drill through needs to be clamped to that. Most of the time, when you're trying to hold a piece there and you drill into it, it's gonna spin. You need it clamped down because the drill bit is gonna bite into it and immediately try and spin the work instead of cut through it. So we generally use scrap wood underneath the piece that you're cutting so that you don't cut through the table. The drill press is designed to the table have a hole in it and the drill press goes through that, but sometimes the table is moved or it's not set up accurately or there's other stuff in the way like the vise that's there, and you want to make sure that you are not drilling through the table or drilling through any equipment that's used to clamp your piece of material to the table. Make sure you remove any scraps that are on there with a brush and not by hand. So for example, if you're cutting through a piece of aluminum, normally there'll be aluminum scraps. You want to brush that away and clean the surface instead of scraping over it with your hand so that those flakes don't get stuck into your hand. It's the same thing with wood. It'll probably be small, like pieces of wood, but they won't really splinter, but every once in a while you'll get splintery wood in there, and you really don't want to clear that with your hand. You want to make sure you're cutting at the right speed. So for some material, you want to cut at a different speed. That's more specific to, again, the bit you're using and the material you're cutting through. And you want to make sure you're doing that so that you're not, cutting super slow through a piece of material. It could be dangerous. And you never want to slam the press down. You don't need to go inchingly slow, but you don't want to slam the press into the material and go at hyper speed when you're drilling through it. And you want to make sure you wait for this machine to stop spinning before you reach and try and clear out any material. Also, I believe one of the drill presses in the shop actually has a slow release to it. So when you release the handle, it goes up slowly, sort of like closing a door. It's critically damped so that it's not just going to fly all the way back up, but not all of them are like that. So we make sure when you're releasing that handle that it goes up slowly and doesn't slam into place. You want to also make sure that before you use a bit in the machine that bit isn't broken or damaged. That could cause the bit to crack when you're cutting through material and launch shards everywhere. And you also want to make sure any guards that we have are in place when you're using the machine. Bandsaw is a piece of machinery in our shop that gets a lot of use out of it. So it's really important that you're operating this machine safely and you respect it and respect people who are using the machine. So the blade guard is the piece that covers the blade and it sort of holds the blade in place and keeps it from wobbling. So the bandsaw is a continuous loop of cutting blade that's in that machine, and if it's not held in place properly, it will flex and bend. So you want to make sure that you're using the least amount of bend and flex as possible to be making sure that you're not going to flex that blade in a way that it's going to break. So the height of that blade guard needs to be 1/4 of an inch above the material that you're cutting, and it needs to be locked in place. Normally there is a turnkey on one of the sides of the bandsaw, and that needs to be locked in place so that it doesn't move up or down. You want to keep your hands as far from the cut as possible, and you never want to cut small material. And what I mean by small material, I don't mean thin material. I mean a piece that is very small. So if you have a square piece of wood that is 1 inch by 1 inch, you really don't want to be cutting that or anything smaller than that on the bandsaw necessary. When you're cutting something circular or rounded, so for example, if you have a parabolic curve that you have marked on a piece of wood and you want to cut that out, make sure you make relief cuts. And relief cuts are straight cuts that go into the edge of the curve. And then you're cutting out essentially tiny pieces of material instead of one long curve. So they're sort of lines that would normally be not tangent to the curve, but straight against the curve of the side of a semicircle. And then you're cutting through all of those instead of just one line of the semicircle. If you ever need to stop cutting, so let's say you're cutting a straight line into a piece and you decide, oh, I need to stop and then cut through the other side. Make sure the material stays where it is in the cut. You turn the machine off, keeping the material in the same place. Wait till the blade stops, and then you can back it off from the blade. Never back a piece of material off of the blade while it's running. It's super dangerous. You risk breaking the blade. You risk messing up your material. It's just not a good thing to do. You also don't want to use excessive force. Don't slam stuff into the saw blade. That's dangerous. You don't need to be, pushing anything through at hyperspeed. It's going to cut. Don't be super slow either as to just sit there and burn material like wood. But again, you don't need to be flying through stuff. Just go with the cutting speed. You'll be able to feel it when you use the machine. And again, remove any scraps with a brush and not by hand. All right, next is the table saw. So the table saw is a really useful piece of machinery that, again, gets a lot of use, especially when we're making field elements. So you want to make sure that all guards are in place before you start the machine. Our table saws have a guard, it's like a clear plastic guard that goes over the top of the saw blade so that the saw blade is never out in the open while it's cutting. That is really important to have in place. It'll slide out of the way when you move stuff through it. It needs to be on there. You want to make sure your blade height is roughly 1/8 of an inch above your material, or about like 1 sawtooth height above your material. So what you'll do, let's say you're cutting a piece of wood, you'll slide your piece of wood up against the saw, you'll turn the knob on the table saw until you see the blade rise about 1/8 of an inch or 1 tooth of height above that material, and then you'll keep it there in that place. And you can lift the guard up for this reason, and then you have to lower the guard back down when you do that. You want to make sure you keep your material absolutely as flat as you can against the table to avoid kickback. So what kickback is, when you're pushing a piece of wood into the saw or piece of material into the saw, and it's not level on the table, the saw is spinning so fast and has so much grip that it is just going to grab that piece and launch it right back at you. If you're cutting through and the saw is actually making it all the way through the material, you're keeping it flat and you're pushing it straight, that shouldn't happen. You should never get kickback. But if your material is riding up onto the saw, it's almost always going to kick back. You want to make sure you're using the right guards for the right job. So there's guards in place for ripping and cross-cutting. So you need to make sure you're using the right one. In this picture here, in the bottom right, it's kind of on the text a little bit, but you can see that there's a guard on the side there. That guard locks in place and allows you to make a straight cut. And again, that's keeping you from holding your hand in that one spot. You also want to make sure, again, the material is flat against the guard and is in place. So the guard is useless if you're not actually pressing the piece of material up against that guard. Also, push sticks are one thing that we use to keep your hand away from the blade. It's essentially just like a wooden or a plastic stick that pushes down on the board, and you can use it to push through the blade. So it keeps your hand away. If you have a lot of material in between the guard and the blade, you can use your hand. But when you have less than probably 6 inches of material, I'd suggest using a push stick. And the table saw is arguably one of the most dangerous machines in the shop. It can cause kickback. The blade is spinning very fast. It's exposed. You want to make sure you are treating it with the respect it deserves. You need to make sure all the guards are in place. You need to make sure that you have people, standing away from the machinery when you're using it. You need to make sure your hands are moving in the right spot. Your material is flat. Just treat the machine with respect. You don't need to be afraid of it, but just know that it is a dangerous machine. So in our shop, we have 2 chop saws. We have one that we use in the wood shop for wood, and then we have one in the main shop that we cut metal and material like that on. So they're both fairly loud, but the metal one specifically is extremely loud. So when you're running the metal chop saw, ear protection is required for you, and let people in the area know that you're running it. It's very loud. It's jarring when you hear it go off. So make sure that you're saying, hey, I'm going to go run this. I'm going to go cut a piece of material on this. Use ear protection, and just be courteous to people around you. It's also important to note here, just as a general requirement when using any of the machines in the shop, make sure that when you're using the machine, that's what you're focused on. If you see someone using a machine, don't call their name, don't scream at them, don't horseplay. It's very serious. Someone can turn away, and then the next thing you know, they're cutting something they're not meant to be cutting. So any material that you cut in the chop saws, you need to make sure it's clamped down and it's tight. You need to make sure it's in the clamp, and then you can check to line it up with the saw and then lock it in place in the clamp. So the metal chop saw has a sort of sliding clamp on it, or vise, and you can use that. And the woodworking chop saw has a clamp that comes from the side and wraps around and locks down onto your piece of material. So you want to make sure there are any cords or fingers or anything out of the cutting path of the blade besides what you want to be cutting. So make sure that, again, the cord of the saw isn't draped over the cutting area. I know that sounds silly, but it happens. You want to make sure, again, your hands are out of that cutting space. So normally chop saws, like I know the wood one below, the Walt, I think there's some other brands that have it too. They actually have spots where they'll show you on the saw to place your hands. And the best idea is place it as far away from the cutting area as you possibly can. Yeah, you want to start the saw at the top of its arc. So they lock in that position at the top. And normally there are buttons on the handle that are like there's a safety and then there's a start button on that saw. And you want to start it at the top when the guard is fully engaged. So if you see in that picture there on the bottom right, the guard covering the saw is fully engaged, and that's when you want to start it. You never want to start the saw with the blade exposed. So you start the saw on the top of that arc and you pull it down into your work and you cut slowly, applying pressure as you move through. So you'll feel it catching the material and you'll cut right through. Blade's spinning fast, so it should cut through easily. The metal one is a little bit different. It feels totally different, and depending on what you're cutting, it'll slide through. So you want to, once you make that full cut and you come to the bottom of the arc, when you're done cutting, you want to release the safety and the power button. The saw is slowly going to spin down and stop spinning. And then once it stops spinning, you're going to release it, pull it back up to the top of the arc, and then remove any material. You never want to reach in when the saw is still spinning, even if it's like cut off, it can still cut you. And the last thing we're going to worry about is the lathe. So most, if not all, injuries from the lathe come from entanglement. That means that there's hair hanging down, there's something like baggy clothes getting in the way, someone's hand gets in the machine. The lathe is spinning at a very fast speed. It's spinning very accurately, so you need to keep loose items away from the machine and tied up, even if you were nearby. Even if you're not the operator of the machine, if you're near the lathe, make sure that nothing is hanging down from what you're working on near the lathe. The lathe is a really special piece of equipment. It's very unique, and it's going to be used by designated students. So obviously, if you want to use the lathe, if you want to learn how to use it, someone can teach you how to use that. But it's not really a machine that we want everybody standing in front of and working on. It takes practice, and it's very specific how you need to use it. So we ask again that if you want to use that machine, that you ask somebody or you're someone that's trained on it. You want to keep the working area of the lathe free of scraps and tools. Tools can get in the way when it's spinning and get launched out of it. You really want to keep that machine clean, and the students that use it take good care of it and try and keep it that way. Make sure the machine is off before you mount or remove any accessories or material. So again, it's spinning very fast. You don't want to be attaching anything while it's spinning. That's a horrible idea. You don't want to be inserting any material while it's spinning. That's a horrible idea. And we also have a CNC machine in the shop, and that's sort of like the lathe as a specialized piece of equipment. And that's something that you can get trained on, but it's not really something that any student can just walk up to and use any time of the day once they've been trained on it, like the bandsaw. Like the bandsaw, if you're trained on it and students have to go cut something on that. But the lathe and the CNC are different. All right, does anyone have any questions they want to type in the chat that I can answer?
All right, that about wraps up this entire RoboU. I hope you guys have a good Thanksgiving. Please keep in mind that there will not be a RoboU next week, and that's because Thanksgiving is next week. But there will basically the programming RoboU is being moved to the week after Thanksgiving. So after next week, that Saturday is when programming will be. Do keep in mind that. But I hope you guys have a good day and a great Thanksgiving. Hope to see you next RoboU. Bye-bye.